We're looking at two AP problems in one right now because in 1979 and 1987, they defined f of x to be the fraction 1 over 1 minus 2x. And then they asked some common questions. For instance, find the first four terms and the general term of the Taylor series expansion of f of x about x equals 0. What they could have said is it could just been a Maclaurin series because then the center would have been implied to be 0. So if you've got a Taylor series, I think the first thing you need to do is you need to compute the Taylor series. And that will require you to get the nth derivative. You'll need to plug in your center 0 into the nth derivative. You'll have to divide that then by the nth factorial and then multiply it by essentially the quantity of x raised to the n. And if you're familiar with the process I do here, then you'll recognize a table when you see it. And we got here negative 1 over 2x minus 1. Oh, that was that quotient rule. Oh, and we got the chain rule. Oh, that's going to be ugly all the way down the line. Now the numbers aren't bad, 1, 2, 8, 48, but then I got to divide them by factorials and multiply, and it kind of becomes a mess. And the issue I have here is I'm not sure if I'm going to be able to figure out the general term that way. Now, what would happen if I would have, I don't know, let's simplify all the simplify all the factorials first. Wow, all the numbers become much simpler. 1, 2, 4, 8. Very much a pattern there. And in fact, if you multiply 1 by 1, 2x, you can actually determine that it goes 1 plus 2x plus 4x squared plus 8x cubed. You could even figure out that the general term is essentially 2 is being raised to the n and x is being raised to the n, and that's how you can write our summation formula. And congratulations, you can get that answer if you choose to do, well, the table method of finding out all the derivatives. Or you could come back to here and realize that looks like a power series, and more specifically, a geometric series. A geometric series whose first term is 1 and its common ratio is 2x, which means I don't have to do all this work over on the left. I could have just said, here's my first term, it's 1. I could have then multiplied 1 by 2x and just say plus 2x, and then just realize I'm going to keep multiplying by 2x each time, which is the same as 4x squared 8x cubed. But if I leave it as 2x quantity squared, 2x quantity cubed, I could rewrite the summation as 2x quantity raised to the n. So both of these are acceptable answers, but as you can see, method number 2 went a lot faster than method number 1. Question B reads, find the interval of convergence for the series in part A, show your method. Since I just did all that work for part A, I figured I would leave it on the screen so I could see the expanded series and the various sigma notations. And so that's kind of helpful because if I'm going to do the interval convergence, I might consider using the ratio test. And the ratio test requires you to set up a limit as n approaches infinity of the absolute value of the next term, in this case 2 raised to the n plus 1, x raised to the n plus 1, being divided by the general term, which you find in sigma notations, 2 to the n times x to the n. And then you simplify that, and because that's just geometric pieces, you will get the limit as n approaches infinity of the absolute value of 2x, which just works out to be the absolute value of 2x. And for it to converge, that must be less than 1. So if we then go ahead and divide both sides by 2, we can say that it will converge as long as the absolute value of x is less than 1/2. Problem is, with ratio tests, it doesn't tell you what happens at the endpoints. So we'll first plug in -1/2 into that sigma notation. Thank goodness I wrote that up there. And you plug that into the x, and as you can see, I'm going to have 2 raised to the n times -1/2 raised to the n. You know, I could merge them if I looked at the one on the right and just come up with -1 to the n, which when expanded starts off as 1, then you subtract 1, then you add 1, then you subtract 1, and its partial sums go 1, 0, 1, 0, 1. That doesn't go to anything. That diverges, which tells me this endpoint does not get included. So now we do it again with the half. And so we go 2 to the n times 1/2 to the n, which ends up being 1 raised to the n, which is 1 plus 1 plus 1 plus 1, and its partial sums go 1, 2, 3, 4, 5. That just also diverges. And none of the endpoints are included, which I could have probably realized immediately if I would have again remembered that this is a geometric series. and it had a common ratio of 2x, and therefore the common ratio says that it will converge only if the absolute value is less than 1. And the endpoints are never included. So I should have immediately realized it should have just been from negative half is less than x, which is less than a half, and then you could write an interval notation if you wish. Part C consists of 2 questions. First is, find the value of f at x equals negative 1/4. We can figure that out immediately by substituting in negative 1/4 into x, which will then go into f of x. And so we'll go 1 over 1 minus 2 times negative 1/4. Now negative 2 times negative 1/4 is positive half. So our denominator is 1 plus 1/2, which works out to be 3/2. And when we go 1 over 3/2, we can rewrite f of negative 1/4 simply as equals to 2/3. Now I'm going to refer to it as the value of s, but I'm going to need a little time to explain that. So let's move on to the second part. How many terms of the series are adequate for f of negative 1/4 approximating with an error not exceeding 1%? Justify your answer. Okay, so if you're a little bit confused and not sure where to go with, let's first focus on the word error. We know we're about to make an approximation of f of negative 1/4, but we also know that the answer of f of negative 1/4 is already 2/3. So whatever amount we're away from that 2/3 with our prediction, that's going to be the error. But in this case, I want to make sure that my error is no bigger than 1% of the original or the actual amount. So what I need to do is I got to take 1% of 2/3. Now 1% is 1/100th. So I'll multiply 1/100th to 2/3. I'll come up with 2/300ths, which is the same as 1 over 1/50th. So you'll notice I wrote r of x. R of x is a remainder. And all the error is the remainder of what is known as the absolute value of the difference between the actual sum s. Okay, so there's the s, and s is 2/3. And in the nth order Taylor series approximated by t sub n over x, and okay, now I'm a little confused, huh? Okay, I know sometimes math notation isn't the easiest to follow along, but I think in this case it'll actually make a little bit more sense. R of x is the error. How do we get the error? Well, first off, we only want to look at positive errors. So we're going to put it in absolute value. That's all. Okay, just going to make it positive. S is the original, is the actual amount. In this case, 2/3. We know that the answer is 2/3. Whatever Taylor series polynomial we use to approximate, we'll subtract that from 2/3, and that will be our error. And so what we want is an r of x that's going to be less than 1/150th. Okay, now how are we going to get to that stage? Well, first off, it would really help to understand that we are dealing with x equaling negative 1/4. And so if we actually plug that back into one of our sigma notations and go 2 times negative 1/4 and take that quantity and raise it to the n, you can rewrite the sigma notation specifically when x is negative 1/4 as the summation from n equals 0 to infinity of negative 1 to the n, remember that, times 1 over 2 raised to the n. Now the negative 1 to the n, you might recall, means alternating series, which is really important here because we can not only show that this alternating series is decreasing, we can also show it has a limit of 0, and therefore it meets all the qualifications of an alternating series test. Now, the reason why it's important to know it's an alternating series and meets the test is we also might remember there's an alternating series error bound rule. And the rule says that if you want to know what the maximum error is of your predictions when it comes to an alternating series, just look at the next term. So that's in fact what I'm trying to do down here. My remainder of x, which is going to always be less than the next term's absolute value. And since the next term's absolute value is going to be 1 over 2 raised to the n plus 1, which is just literally the next term based on the geometric series that we came up with just a few moments ago, we need to make sure that number is always less than 1 over 1/50th. Pretty wordy there, but in the end, I'm showing that a remainder is less than the next term, which is then going to be less than the rule that I want, which in this case is 1 over 150. So if I can solve 1 over 2 raised to the n plus 1, which is less than or equal to 1 over 150, I'm good to go. And so that's what I'm going to do. I'm going to, cross multiply, get 150 is less than or equal to 2 raised to the n plus 1. Now you can guess and check all you want, or you could just do a log and realize that the log of 150 base 2, which is 7.2, is going to need to be less than n plus 1. So finally, I subtract 1 from both sides, and I come up with an expression that says, or an inequality that says, 6.2 is less than n. So what does that mean? It means that the smallest integer that's greater than 6.2 is 7. That also means that that will be the order of my Taylor series. That is the least number of terms that will produce a guaranteed error that's less than 1%. The problem is that's not the answer to the question. The question asks you how many terms of the series. And since we start our series with a 0th order, if you actually get up to the 7th order, that's 8 terms. And that's the answer to the question. So although n is going to be 7, that's the order of the polynomial. The question asks how many terms of the series, and that's why I'm going to need to say I will need 8 terms to guarantee accuracy within 1% of 2/3. So you've decided to move on from the last slide. Maybe it's because you watch it so many times you have it memorized. Maybe you watch it a couple of times and shake your head and going, I don't know what's going on, and maybe I should just move on. Or maybe I just did such a fantastic job with my presentation and explained it so well that you have crystal clarity and understand all aspects of it. Let's just move on to part D. Use partial fractions in the result from part A to find the first 5 terms in the Taylor series about x equals 0 for g of x equal 1 over the two quantities 1 minus 2x and 1 minus x. I can tell you this problem's a lot nicer, or at least easier to pick up on. But first we need to set up partial fractions because it says do so. And so I set up as a over 1 minus 2x plus b over 1 minus x. And when I multiply all the pieces by 1 minus 2x and 1 minus x, I can rewrite it as 1 equals a times the quantity 1 minus x plus b times the quantity 1 minus 2x. I will need to substitute some values of x so that hopefully I can cancel out maybe some a's and b's. Let's cancel out the b first by plugging in a half. What I'll be left with is 1 equals 1 half a. Multiply both sides by 2 and hey, lo and behold, a equals 2. We can do this again if we plug in 1. This will cancel out the a from the problem and we'll be left with 1 equals negative b. Divide both sides by negative 1 and you get b equal to negative 1, which we can now plug into our original setup. And instead of looking at 1 over the quantities 1 minus 2x and 1 minus x, let's look at it as a subtraction problem. Let's look at it as 2 over 1 minus 2x being subtracted by 1 over 1 minus x. Now, the reason for that is, if you recall, a lot of things I kept saying over and over again is you can think of these as geometric series, okay? And you can think of each one of these having their own first terms, and you can think of them each having their own common ratio. So if we thought of 2 over 1 minus 2x, we could look at it as 2 times 2x, which is then multiplied by 2x, which is then multiplied by 2x. And we can just simply say 2 over 1 minus 2x will equal 2 plus 4x plus 8x squared plus 16x cubed plus 32x to the fourth. And it said 5 terms, so I'm not going to go any further there. But then I'm going to want to subtract a second geometric series whose first term is 1 and common ratio is x, which would then produce a 1 plus x squared plus x cubed plus x to the fourth. And so really all the problem is saying is, what are the 5 terms? Well, 2 minus 1 is 1, 4x minus x is 3x, 8x squared minus x squared is 7x squared, 16x cubed minus x to the third is 15x to the third, and 32x to the fourth minus x to the fourth is 31x to the fourth. And that would be a way to write a Taylor series for our complex little fraction that was written in part D.